welcome everyone, and welcome to my talk. Cut my task into pieces. This is concurrent mode. So today's talk will be mostly about performance. As always, I like to talk about performance, and of course, this is an Angular meetup. I've prepared a demo in Angular, and I will show you some techniques that are applicable within Angular, but they should also be applicable for any other JavaScript-based front-end application. So, did you ever think about what happens when a user interacts with your application? So technically, what happens in the background? The browser, like before we want to cut something into pieces, let's first unravel what we want to cut into pieces, right? The browser will create a task for you. So a task is any discrete piece of work that the browser has to perform whenever you want to, for example, react to a click binding. And this is what's happening. Like you've seen the user here, he's clicking, so you want to react to any click binding here. So let's take a closer look at that. So the gray box on top you see here, this is the thing that the browser will produce as a task. The first row here in yellow, this will be the browser event or the user event that was kicked off and what you probably have a listener on, because otherwise there would not be any script execution, right? So you have a click listener in this case, and on the click listener, your application code, and this is the other color here, and note those colors when you inspect flame charts can be random, but from the color you can determine which scripts they belong to. So every blue color will be from the very same script JavaScript file, and every, for example, pink color would also be from the very same script source. But anyway, you have your application code here, and in this case we're executing first work, then other work. And you see on the x-axis, this is time progressing, and on the y-axis, you see the stack trace. So your method is work, and whatever is executed down here is happening within work. So you may choose to run Lodash or something in the background. So at this point, we maybe Lodash. And in the end, you have this purple and then the greenish colors that indicate actual browser work is going to happen, like rendering and paint stuff. There are not only tasks, but there are also long tasks. So a long task is any task that exceeds the limit of 50 milliseconds. So in this case, we have a 64 milliseconds task. So our blocking time, that's the red thing you can see here, so that one here, is considered to be 14.9 milliseconds because 14.9 milliseconds is the thing that we exceeded the 50 milliseconds threshold. And this is considered as blocking time added on top of your task. It looks scary, right? Because it's red. Red is always scary. But why should you actually care? Well, there is this very new metric introduced in, let me close this one here, introduced at the 12th of March in 2024, so not so long back ago. And this is a metric that indicates how fast is your application responding to your users' inputs. So whenever you click something, you scroll something, you drag something, you change an input of something, a new INP will get spawned. And INP, let me tell you something about this, is reckless. Because it's not only that you have to optimize something, you have to optimize everything. Because the worst ever interaction you have on your page will be counted as INP. So if you have 1,000 good interactions and one bad, the one bad will be your INP thing. That's crucial, it's reckless, but that's how it works. Technically, for very large enterprise applications and for thousands of interactions, the browser tends to strip out some of the outliers that are super high, like 20 seconds or something, and will erase it. But for most of the applications, it's true. The worst ever interaction for a user session will be your INP value. So it's very reckless, and you need to consider to improve that. So yeah, you have only 500 milliseconds in order to not be poor. 500 milliseconds is a blink of an eye. So let's dive into INP. INP is divided into 3 stages. We have input delay, so the time it takes for the browser to finally start processing what you actually want to process. Then you have the processing time, so in this case, the click. So you bound something to the click listener and you do some work. That's the processing time. And then you have presentation delay. So while processing something, you might added a class to something, or you changed styles for some elements. You added the DOM element, removed the DOM element, whatever. The browser has to restyle and recalculate your layout. So this is the presentation delay in the end. Before we go into a live demo about that, let me quickly introduce myself. Hi, my name is Julian. I'm performance engineer at the company Push-Based. Michael introduced it very well before. There, I'm also trainer and consultant, and for this talk, it's maybe more interesting that I'm also RxAngular core maintainer. So without further ado, let's go into a live demo about INP and long tasks. I did not meant to do that. I want to go back here, because I can just switch to here, where we have this beautiful demo application where it currently says this is blank. Is it readable? Like also this part is crucial for like the back rows. Otherwise I can just zoom in a little bit. Let's zoom in that one and also that one. Looks good. Good? Cool. Okay, what I'm going to do now is I'm going to navigate to the route that says native. Before I do that, I will not go here. I want to go to the performance panel and set my CPU throttling to 4 times, because then I can show you how it would work on a mobile device instead of this like very modern laptop. So let me go back to the console here. So I just click the native button here, and as you can see, it yells at me in dark red. It's poor. Web Vitals. This is, by the way, a Chrome extension you can install. It's called Core Web Vitals or Chrome Web Vitals, something like that. And it can give you outputs about any Web Vital in the console. So what has happened here? Let's dive into that. Should be back to the blank page now. Wait a second. Blank page again, full screen mode again. What I want to do here is show you one performance recording of that. Going to navigate over, stop the recording, enlarge it a little bit, and then let's take a look what's happening here on the main thread. We see here 1 second of one big task being executed. So this is what Angular does in the background for us. It takes chords detect changes, and then if we zoom in here, we see header work, sidebar work, content work, and this is essentially building up this whole layout here. So we have for the header, for the sidebar, for the content, and for the footer, one individual piece of work that needs to get executed at a single point in time, because you bootstrap the whole component, everything gets bootstrapped immediately, and we see a big hit on INP here. Again, if I open the console, we can see here this over 1 second point in time. So what options do we have now? We have this big script that gets executed at once. It takes over a second to compute. It's brutal, right? We are smart. We can schedule that thing away because we have a click binding, and then we say, okay, we move it away, make INP look great because we only spent a millisecond on the click, move the big work away from our click timer. What options do we have for scheduling? So there are timer APIs like set timeout or set interval. We can use request idle callback. We can use the message channel. This is maybe something new for many people. This is a channel you can use in order to cross communicate between tabs. So if you want to synchronize data between multiple browser tabs, you can use the message channel. It will also schedule things. You can use the animation frame or the new scheduler.postTask API. Whatever you use should be working, because this is right now our INP, right? We have one single task that is a brutally long, 1 second long task for just this one click event listener. But I said we are smart, so we install a timer here. The click event is now, I don't know, a millisecond or so. We install a timer, and then we let the long task run at a later point in time. And this is how we can achieve a very good INP metric at first glance. So let's take a look at how this looks. Let's first look at the code. So we have essentially here this A tag, where we have a click listener on, where it says nav to native scheduled. What are we doing here? We just use set timeout in this case, so a timer API, and then call our router, this router navigate to the scheduled route. Let's look at the application. And just as a reminder, I have still, this is why we have the exclamation mark here, the warning sign, I have still throttling enabled. So let's take a look at the console and click the scheduled button. We see here interaction 24 milliseconds. It's beautiful, right? Like our INP improved. We're geniuses. Let's take a look at the flame chart. Click it. Let's take a look here. We see here now in this interaction pane here on top, this tiny little pointer event here. This is our INP, 30 milliseconds. 30 milliseconds. And then we see our brutally long task here, 1 second, just executed at a later point in time. Okay, so yes, it works, but what does happen if a user clicks here in between? Like we have a new user input while we are executing this super long task, right? I have the feeling there's still like a huge elephant sitting within the room. So let's address it. First, let's explain it. Now we are at the stage here where we have our blocking task. The new blocking task is now adding up to our input delay, because yes, the browser is aware a user wants to click, and you can like rage click as often as you want. The browser will be aware of it, but it cannot execute it because there's a blocking task. It's running here, and it cannot do anything about it. So you have this piece of input delay now added on top of your INP value, and then it can start process the click, and then it can start the rendering, and then you have your final new INP value. Why is that the case? In order to get an answer to that, let's dive into the JavaScript event loop. Just a little bit. Not a very deep dive, but let's explain it a little bit. So within the JavaScript VM, there's an endless loop going on. It's a while loop. It asks for give me tasks, and whenever I have a task, execute it away. So far, so good. What is this queue? The queue is the macro task queue. So what is a macro task? All of our timer APIs we have talked about before, so timer, idle callback, message channel, request animation frame, and essentially any other browser API, like resizing, input change, mouse down, mouse enter, mouse leave, whatever you know from the browser that can emit an event, will end up as a new macro task in the event loop. Also, of course, third-party extensions like Grammarly or 1Password or LastPass or whatever. For example, you click in an input box, your LastPass extension will then like render this tiny button and this dropdown for you. And this also runs on the same thread and will be also added as a task into your macro task queue. So yeah, let's take a look at that. And the model it has behind it is the run to completion model. So before any other task can be like tackled, starting to get executed, any before task needs to be fully done. Otherwise, it cannot start the next task. And this is the run to completion model. So let's go through it. We start with script evaluation. So our front end is now loaded. The user, in the meantime, clicked. So we added mouse down and a click event to our stack. On mouse down, we want to execute work and work 2. And again, on the y-axis, you see the call stack, and on the x-axis, you see the time passing. So we have to execute work and then work 2 here. Then the click happens. We take that from the stack now. Do something on click is being executed. Finally, we end up at the timer fired because someone had said set timeout 0 and then scheduled something in the future, and then we have timer fired. But yeah, the user wants to constantly interact with your page. What happens if something is getting executed here? Well, we run into a problem because, again, we will have input delay. Mouse on the slides. Yes, here. Again, we receive our input here, and then we have the input delay starting exactly here and adding up to your INP value, because INP is measured from that very moment in time and not any later. So yeah, INP is definitely impacted by bloating up your main thread with long tasks. So it's not just as simple as putting set timeout to any href link and schedule the thing away, because whatever happens being a long task will block anything else while it's being executed. So let's take a look how this is actually, and I did again the same error as before. Let's go back to the slides. Yes. So let's go back to our application here. Again, we are on the blank page. We still have a throttled device here. And I think it would be sufficient to just do a refresh, F5. Yes. So everything is refreshed. Now I will go. Perfect. To the scheduled page. Maybe I will add a little bit more throttling because then I can play around a little bit more. So 6 times throttling now. Open up the console again. I click the schedule button, and in the meantime, I'm just clicking randomly on the page. And this is what you see now. Need to point with the mouse. That was my initial interaction here. 1.2 seconds. It was also recorded as INP because this is the longest thing that happened. But all the other interactions here in between, 1000, 800, 700, 500, all of them were recorded because I was just clicking randomly on an empty space while the main thread was blocked by executing something else. And this is how you can also mess up your INP value, because something is going on in your application in the background. It's not rendering anything, it's just doing something. The user tries to interact with your page, even if it's a loading spinner and you try to build something big in the background, it will be recorded, it will be sent as INP to as a metric. So the best goal is to not have so long tasks, right? So question is, what to do with our long tasks then? So my friend Kirill proposed a nice little game. Maybe some people of you know that back then from the Game Boy times, where you played this nice little game where you could just like destroy your flame charts like this. But unfortunately, it's not working out like that. So I've come up with 3 different ways on how to improve your long tasks. First thing, most preferred solution whatsoever, and one wise man, I think it was Paul Lewis, said once, performance is the art to avoid work. So reduce whatever you're doing, like reconsider what you are scripting there, and if it's not needed, remove it. That's the best thing you can do in any case, especially for slower end devices. Most of you in your working environment, you are working with like MacBook M3 Max or whatever. It will compute anything away. You will never notice any JavaScript bottleneck because your machine is so highly powered. Throttle your device down and see how it behaves then. And then you know how people on mobile devices will see your application actually working. But yeah, it's the preferred solution. It's very high effort. Sometimes it's not even possible because like, work has to be done. So what other options do you have? You can distribute your work. So chunk it down into smaller pieces, distribute it on the main thread, give the browser time in between to interact with your users. And then in the end, if you have distributed it, you want to also prioritize it because like some things are more important than other things. Sending data to the IndexedDB is maybe less important than displaying the new pop-up on the screen for users. And that's where I need to introduce you to RxAngular Concurrent Mode. This is what the talk is all about. So we have 4 conceptual building blocks here. The first 3 are targeting the distribution part. The last one is targeting the prioritization part. First thing is scheduling. We learned already about that. We can schedule things like tell the browser, do something in the future, but not now. First render stuff and then do something. Second part is chunk it into slices and then execute them bit by bit. Then you want to control the size of the chunks because it should not be random, right? You want to be aware of what frame budget you want to target and how big of the chunks you are slicing up because it creates overhead. And then finally, we have prioritization because some chunks are more important than the others. So we want to move it around on the main thread. So scheduling, the first technique, we've already talked about that. You use one of the scheduling techniques to install any scheduler, move your work away from the actual interaction. Then the next thing is chunking. So yeah, we have this big click event listener. Why can't we just split it apart into 3 pieces and render them bit by bit? None of them are long tasks now. And for every task, we have time here in between. Oh, time here in between to interact with the application again. So yeah, user can react to input. The browser can react to input. So consider the following setup, that what you've seen before in the before 2 demos. So we have 4 components being rendered here: a header, a sidebar, a footer, and a body. So now we want to apply chunking to this. We have seen before in the flame charts, we have header work, we have sidebar work, body work, and footer work. So why not just slice it just here? It would make sense. And just then chain them together. It's super easy right now because you can just import this nice little neat directive, which is called RxLet from the RxAngular template package. And instead of rendering all the components at once, you just use the structural directive RxLet with an empty input whatsoever. This is just for demo purposes. In real world, you would obviously bind some reactive state to it, but for now, for the demo purpose, just give it an empty input. It will also do the job. We can also do the same for lists. So lists are anyway the most big problem for applications, rendering hundreds of components at once. You don't need to render them at once. You mostly need to render like a tiny proportion of it at once. So yeah, whenever you render lists, you have item, 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 item until the whole list is depleted, and then yeah, the browser has to paint and render all of it. But you can use Rx4 from the RxAngular template package. So instead of using ng4, you just use Rx4, and what it does for you, it slices the item templates into tinier pieces, rendering them bit by bit. But it's not dumb by any means. It's a little bit smarter, and you can configure how it works in the background because it's not creating one task for each individual view. It wouldn't make sense because sometimes you have like very simple list items that don't require much work and would create too much overhead to render every one of them in a single chunk. So you just define a frame budget where you say how many views should be rendered together in one chunk until I start creating a new chunk for you. So by default, it's configured for 60 FPS. How does the algorithm work in the background? So it executes one view, measures the time, sees, okay, I have still time left. I didn't hit the threshold. Give me the next view. Give me the next view. And now it notices, okay, I exceeded the threshold, and now I need to spawn a new task. So now I pause whatever I was doing, give the browser back time, and then I restart the queue with whatever task is being left. So this is how the implementation, like in a very simple way, looks like in the background. Whenever you have a task, and while the runtime is still lower than the threshold we have defined by the frame budget, give me the next task, execute it, and add the time it took on top of the runtime, and then repeat. So let's take a look at how this is looking like. Again, I'm so used to closing the browser. Before we dive into the code, into the application, let's first dive into the code. So I have my concurrent component here. So maybe let's start with a native one. So yeah, that would be the native implementation. We have header bar component, sidebar component, main content component with an ng4 rendering list items, and then a footer bar. If we go to the concurrent implementation, we have now RxLed for the header, RxLed for the sidebar, RxLed also added to the main content, and then for the footer. Let's see how this is behaving. So I go back to the blank page, I close that, maybe I do a refresh so that we can see a fresh INP value. So I click to concurrent now. And you can see this is 6 times throttling. We have INP of 104 milliseconds, and you could visually tell that the pieces were added bit by bit by bit by bit to our application here. I also told you that we can do that for list items. So let's quickly dive into the flame charts here. Take a look at how this is looking like, concurrent. Open this up a little bit more. And there you can see all the chunks are executed bit by bit. So first chunk should be header bar. We can scroll down and take a look at if this is true. It says header work here. Then we have sidebar work. Then we have content work. And in content work, this is something I wanted to show you. This is added on top because here we render our list templates. So we have content work here. And content also includes the list of items. And I told you we can improve even that. So let's go back to the code, and instead of ng4, we use rx4 here. Save it. Go back to the blank page, go back to concurrent, and now you could see that all of the items here were added bit by bit by bit. Now we have 100 items. We can also see that in the flame charts. Remember this view here, where all of the items are rendered here at once. Go back to the blank page, start the recording, go back to concurrent. There you could see all the items are added in. And now, if it lets me zoom in a little bit or scroll, yes, perfect. We see now the content part, which is this one, has not only content, but no list creation on top of it, because the list creation happens, as you can tell, here. So list items are here, generated bit by bit, and as you can see here you now see the frame, the FPS configured. So 90 milliseconds, 11 milliseconds, 20 milliseconds, 90 milliseconds. So it tries to really do the best it can to fit into that frame budget, so executing tasks bit by bit by bit. Okay. Last thing I want to discuss here is the priority. So before, or right now, we executed first header bar, then sidebar, then body, then footer. But the most important page, part of your page will be body, for sure. So what you actually want to do is move body from the third place here to the first place. So you want to change priority here, regardless of the way how you define it in DOM, because this is how it works naturally, right? So the way you define it in DOM, that's the prioritization you get. But you can also configure that. That's what you want to do here. So there are 5 different priorities. It's a little bit more than just a number, but I won't cover everything here. So right now we treat it just a name is according to a number. So immediate would be highest priority, do it immediate. It's still scheduled, but it's the first thing that's getting executed. Then you have user blocking, priority 1. Normal, this is the default behavior. Then low, then idle for something that should run in the background, like it's like for example background IndexedDB updates or something like that. So how can you do that? It's possible to define the strategy just by an input. So for example here for the header we say please render it in strategy low. And the body with immediate, because this is the thing we want to render as the first thing we want to render. And then the footer, also low. You can also put it to idle, for example. This is just an idea. There are multiple ways how to achieve that goal. So yeah, let's take a look at that. First, let's take a look at the code. So this was the example from before. We have just assigned all the let directives and for directives here without any strategy. So if I switch back now to concurrent priority mode, we will see here header bar is now assigned to strategy low, and the main content is now assigned to strategy immediate, and the footer is assigned to strategy low. So with that in place, I can again go here from our blank page to prioritize. And then you see content is the first thing that's added into the DOM and not header bar. That's header bar, then sidebar, then content, then footer. And now to prioritize one, content first, then sidebar, then header bar, then footer, whatever you want. But you can define when things are getting executed. So with that, I'd like to wrap up my talk for today. And if you like the RxAngular library, please leave a like and star us on GitHub. Also, I mentioned my good friend and colleague, Kirill, before. He wrote a masterpiece, like seriously a masterpiece. You have to read it. You cannot click the link, I know, but you will get another link on the next slide. Make sure to read this thing. It will give so much more introduction to INP in general and to the JavaScript event loop. So again, my name is Julian Jandl, performance engineer at the company Pushbased, also trainer consultant. Book us if you love us. Of course you love us. Thank you for your precious time. Slides repository.